Hello everyone. So today we will be talking about mesh analysis. And the purpose of mesh analysis is to analyze circuits using mesh currents instead of element currents, such as the current source. So the process deals with this. We're going to be generated with a loop, and we're going to draw a loop in a closed path, and it has to be closed path. And not only that, but it cannot overcross from one another. So here we have 3 circuits, and we're going to draw as many loops that we need for each one. So this one only has one closed path, so we're just going to draw one mesh current right here, and we'll label that as 1. And then moving on to the second circuit, we have a mesh current right here, another one up here, and another one down here. And we can label that as I2 or I3 and I4. And finally, we have this circuit, which looks pretty odd, but it still follows the laws of mesh analysis. So we'll draw one right here, one down here, one left from here, and another one oddly right here, and we will label that as 5, 6, 7, and 8. So mesh analysis consists of a 4-step process, and we've already done step 1, which is to draw all the closed loop paths of the circuit. And then the second step is to apply KVL to all of the loops. And then after that, when we get our terms for our KVL equation, then we have to consider and assign a sign convention of the direction that the path is entering and exiting the polarity of a component. And if you guys didn't check out my Kirchhoff's laws, then I've clarified that it's really important on what the sign convention is when we're dealing with KVL. And step 4, we're not going to do that yet. We're just going to focus on circuit 1. So circuit 1 is pretty simple. So step 1 says is to draw all the closed loop paths, and there's only one path. So we'll just draw it right here, and we'll label that as I1. And now it's time to apply the KVL to this loop. And what we know by the laws of KVL, Kirchhoff's voltage law, is that the sum of all voltages around a closed loop path is equal to 0. So we know one side is 0, but what about the other side? Well, we have to consider the KVL process of it, and also assign a sign convention of the direction that the path is entering and exiting the polarity of a component. So we'll assume that it is deemed positive when the current, so we'll draw an I here, when it travels from plus to minus. Thus, if so we'll depict I1 as I, so if I travels from plus to minus, then that term would be positive, but if it's the other way around, where the current is traveling from negative to positive, then the term would have a negative sign convention. So we have this path right here, and we'll start off with this term to apply KVL. So we have I1 times R1, which is positive, and then I1 times R2, which is also positive. And finally, we have this voltage here, and it turns out that this path is traveling from negative to positive, so it's going to be negative. And there we have our KVL equation, and we were going to be able to solve the unknown elements from having the knowledge of how to use mesh analysis. So moving on to the second circuit. So here we have the second circuit, and we're just going to draw all the closed loop paths that there are. So one right here, label that as I2, one above here, and we'll label that as I3, and another one down here, label that as I4. And now we shall apply KVL to all of the loops. So let's first apply it to this closed path right here. So we'll have we'll call this, since there's two or more meshes, then we'll just call this mesh 2, and then we'll have an equal sign at one side, and then we're gonna assign a sign convention of the direction that the path is entering, exiting the polarity of the components. So we have I2 going, rotating clockwise, so it passes through R1 from plus to minus. So that would be, we take R1 times I2, and now we've came across an additional rule that I haven't talked about, and that is step 4. And step 4 is to consider neighboring mesh currents. So we do know that this path is entering through R2, and we have to consider I2, but there's also a neighboring mesh current, I3, that is also passing through R2. So we have to consider that as well. So we take R2, and then we multiply by I2, and it is positive because it is flowing from plus to minus. But for I3, it's flowing from negative to positive. Therefore, it's going to be minus I3. And there we get R2. And now moving on to R3, I2 passes through from positive to negative. So therefore, we have a positive here. And then I4 is going from minus to plus. So that would have a negative sign convention. That would be minus I4. And there's our mesh 2 equation. And then our third equation, mesh 3, would be, we have a current source, so we've already determined what I is. So we have simply just I3, so we already know what I3 is going to be, so we don't need to determine what, we don't need to apply what the equation is. And now for mesh 4 includes, so mesh 4, I4 is passing through from minus to plus, so for R3, it's going to be negative I4, and then we have to consider the neighboring current for this, which is I2, so it's plus I2. And then for R4, that would be positive, and then I3 will be passing R4 from minus to plus, so that would be minus I3. And that is it for our mesh equations for our second circuit. So here we are given a practical example with components including numbers, and the question asks us, given that the voltage source is 5 volts, the current flowing through the circuit is 1 amp, and R1 is equal to 2 ohms, determine what R2 is, using the concept of mesh analysis. So let's first draw that closed loop path that we need. We will indicate that as I1, and then we will apply the KVL equation and then assign the sign convention. So we get I1, and that I1 would be depicted as I, so that would be I1 times R1 plus I1 times R2, and then the path is entering through the voltage source from minus to plus, so that would be minus V, and this whole KVL equation would be equal to 0. So we know what the values of voltage is, and voltage is 5. R1 is going to be 2 ohms, so we have 2 right here, and then we indicate all the symbols, and I1 is essentially equal to what I is, lowercase I, and that would be just 1, so 1 times 2 here, and then 1 times whatever the value that we need to find for R2. So we'll just isolate everything to one side that is not R2 to determine what the value of it is. So we'll add both sides by 5. So we'll be able to get rid of this, and then subtract both sides by 2, and then we'll be able to get rid of this, and we are left with 1 times R2, and then R2 we can just get rid of the 1 because the 1 has been omitted. We get 3 ohms, and this is our value of R2 using the process and method of mesh analysis. I recommend you guys watching the next 2 advanced videos that are a building block off from nodal analysis and mesh analysis, and that is Supernode and Supermesh. So I highly recommend you guys checking it out if you guys want to know more about this topic.